So what is an electrolyte? Oh, that's nice. I put the definition there. So anything that, when added to water, completely ionizes, okay, or has some form of ions. That is our electrolytes. And ultimately what you are referencing is that we have electric current, hence the electro, and then light, which is what we were using in lab, just saying light. So if we have a solution that allows for the passage of electric current through it, it could then potentially light a light bulb, right, as a hand-wavy argument for what the name of that or electrolytes are coming from as that term. Right? So we need ions to allow for the passage of current, because electrical current is merely electrons or charge. So as long as we have ions, the electrons can move through our solution, and we can allow for that passage, and hence we've got an electrolyte. So we've got a bunch of different examples up here of things that could be considered in this electrolyte category. So when we consider electrolytes, we've got strong electrolytes, weak electrolytes, and non-electrolytes, meaning they don't allow for the passage of electric current. Okay, so any ideas? Any one of these you're like, ah, that's a strong, weak, non, something like that? No ideas? Okay, maybe I shouldn't ask so quickly. NaCl, I heard was strong electrolytes. We'll just go Se. I heard something about acids. What about the acids?
They are strong.
Which acid?
Sulfuric acid.
Okay, sulfuric acid, also a strong electrolyte. You did mention acids being strong electrolyte, so I want to throw in one little caveat here. HF is hydrofluoric acid, which is an acid. Is it a strong electrolyte? No. How do we know it's not a strong electrolyte? A couple answers we can use with that one.
Because it's not a strong acid, so it doesn't get completely.
Your strong electrolyte means it completely ionizes. So your strong acids, by definition, completely ionize. So if it's a strong acid, it by definition is a strong electrolyte. Right. Your weak acids do not completely ionize. Well, if they do not completely ionize, they are by definition not strong electrolytes. Right. How do we know HF is not a strong acid?
We didn't memorize it.
Okay, remember our definition, unfortunately, it's what it is. Our definition for our strong acids are things that you just have to have memorized. HF is not one of those things you had memorized, so it's a weak acid. If it's a weak acid, then it by definition is a weak electrolyte. We'll just call it WE for this case. Anything else you can classify up there? What was that? Oh, interesting. I didn't even realize I had that up there. We've got acetic acid up there. What would you classify acetic acid as? Okay, it's probably best classified as a weak electrolyte. Okay, we do run into some gray area there, not knowing exactly what's going on with that, and we'll address that issue here in a little bit. But that's probably a weak electrolyte. There is a reason I've got it colored. We'll come back to that reason in a little bit. A whole bunch of other things up there.
So would that, if acids are strong electrolytes, would that make bases weak or non-electrolytes?
So, interesting question going back to the bases. Acids and bases are opposites of each other, and they react with each other. But they react with each other because acids give you H plus ions, cations, and bases give you OH minus anions. Both of them generate ions, which means they should both be electrolytes. So if we have a strong acid, it would be a strong electrolyte. If we have a strong base, it should also be a strong electrolyte. So our sodium hydroxide, also a strong electrolyte. Okay. Other options.
Silver bromide.
What about silver bromide?
Electrolyte.
Okay. Why would you classify it as a non-electrolyte?
Because it doesn't ionize.
How do you know that?
Because you told us once.
I'll kind of half accept that one. Anybody know why you should be classifying sodium bromide as a non-electrolyte? Silver bromide, thank you.
It doesn't dissolve it
Okay, how do you know it doesn't dissolve?
because
Solubility rules. So you'd have to use the solubility rules to say silver bromide is a solid. That's why. So yeah, I did kind of say it, but I said it based off of interpreting the rules. Okay. What else might we throw in there? Oh, it's early, but come on.
iron hydroxide.
What about iron hydroxide?
It's a salt.
It is a salt, which would suggest what?
I don't think it dissolves water.
So we'd have to use our solubility rules again, and we'd have to say what was iron hydroxide. And using our solubility rules theoretically, but I'm not positive on it, comes out that it is insoluble in water, which would suggest non-electrolyte. You guys are going to love the big reveal on this. I'm actually kind of already irritated at myself for it, so we'll just deal with it. More to work with. There's still more.
Okay.
3 more left.
Calcium carbonate is insoluble.
Calcium carbonate is insoluble. How do you know that one? Solubility rules again. If it's insoluble, we would typically predict non-electrolyte. If it doesn't produce ions, it should be a non-electrolyte. How else might you know calcium carbonate? You know that nasty scum that you get in your sinks or your tubs, or sometimes on your glassware, those spots after doing dishes, if anybody does dishes. Okay. Typically due to calcium carbonate. Okay. It's a very insoluble salt compound. Okay. Now what?
The other two are weak.
The other two are weak. Okay, why are you saying weak?
So that follows the pattern.
Follows the pattern is a possibility. Okay, unfortunately, that is a bad option.
Never mind
So it's a reasonable guess. I mean, you're in a situation now where you're allowed to guess. So you guessed. What's your next follow-up? They're not weak electrolytes. There's only 3 options. You're now down to a 50-50. Okay, so we could try strong. And conveniently, strong actually rhymes with your answer there. That is actually wrong. We're looking at
Those are covalent.
non-electrolytes for those last 2. And you'll notice that I do have some kind of color patterns going on with this. Okay? And that color pattern is actually matching different system. Based on how these compounds are typically classified. So let's group through these and try and come up with some rules on it. The strong electrolytes, you were consistently correct all the way across the board. So what's common about the strong electrolytes?
You know what elements on the first column?
Oh, that's interesting. I didn't see that pattern, so let me mess with that a little bit. Let's fix that pattern. Let's turn that into magnesium hydroxide. Metals, there's an interesting question. Sodium chloride, magnesium hydroxide both give you metals, but the sulfuric acid didn't quite. Sulfuric acid was defined as part of the name, acid, and not just that it's an acid. It was a strong acid. Magnesium hydroxide? strong base. Sodium chloride,
Ionic compound.
an ionic compound that in particular is soluble when we hit water. In all three of these cases, these would all be aqueous phases, or aqueous phases, depending on how you want to pronounce that. Okay. So we are looking at strong species, which covers our acids and bases, and we're looking for aqueous phases with these. Okay. Ultimately, in all three cases, what we are forming is a large concentration of ions. Okay. The weak electrolyte one we're going to double back to because that one is actually exceedingly tricky. Let's jump to the non-electrolyte one, which for the most part holds pretty true. What's the pattern that we notice in the non-electrolytes? We have carbon, hydrogen, and oxygen. Let's expound on that. We're looking at non-polar covalent bonds. Okay, for the most part, those are non-polar covalent bonds. We do run into a weird exception with our acetic acid. Whoops. Which could sometimes be classified as a weak electrolyte. Again, depending on the level of information that we're trying to throw at you and we expect you to interpret. Okay? Because it is a weak acid, we can then classify it right away as a weak electrolyte. All acids will form positive charges. Once they've got the charges, we've got an electrolyte. Okay? But our general quick rule of thumb, nonpolar covalent bonds, non-electrolytes. What does that mean our weak electrolytes are going to be? There's a good answer. Everything else. Anything that doesn't fit in our strong lots of ion situation, and anything that doesn't fit in our nonpolar covalent bond situation. Okay. Are we going to run into gray areas through each of these patterns? Absolutely. We already encountered some of those. For instance, our nonpolar covalent bonds, our gray area is that acetic acid, as a weak acid, is also classified, or better classified, why can't I spell? W, that's what it looks like, as a weak electrolyte. The last compound, ethanol, which we may be seeing more of after the final, okay, is a non-electrolyte. At least one person smiled. Thank you. Okay. This other compound, and I have no idea what compound that is, also going to be a non-electrolyte. We're looking at covalent bonds. All of those atoms are very tightly connected to each other because of shared electrons. If they're sharing electrons, you can't form ions. If you can't form ions, you can't be an electrolyte. Because the whole point of being an electrolyte is having ions. Okay? That leaves us in this weird gray area for everything else. Okay? You accurately determined one possible option. You could look at the solubility rules for those three compounds listed through the middle. And if we look at the solubility rules for those three compounds, we said they were all insoluble, which meant they were all solids. I know it was everybody's favorite topic. Remember that guy, Le Chatelier? Vaguely mentioned his name a little while ago. In association with what word? Not London, not a bad idea. Equilibrium. And equilibrium stated what? What was that looking at?
Wasn't it like when you have a product and a reaction? Like, balance, yeah.
A balance between our reactants and our products. They always go both directions. We move from our ions to our solids. Okay? We would also then move, by definition, from our solids to our ions. Would we be forming a lot of ions with these compounds? No. Why not? Because by definition, we've grouped them as solids, so they aren't going to form a lot of ions. Do they have some ions? Yep. If they've got some ions, what does that mean? They're electrolytes. They, by definition, cannot be strong electrolytes because they didn't completely ionize. We don't have lots of ions. But we have a small amount of ions, so we would expect some to show up. Okay. You'll notice HF I classified outside of that category. Okay, I didn't put that next box around it. Why did I not put that next box around the HF? It's not a solid. HF is probably our cleanest example of all of these as a weak electrolyte. Why? Okay. It's still a challenging one. What do we define as our weak electrolyte? Everything else. Okay. Is HF a strong electrolyte? Is it a strong acid? No. Okay. As soon as we moved into that acid or base realm, we have to say it's strong or it's not. Okay. It's not strong, so it can't go into the strong electrolyte category. If we look at the nonpolar covalent bond, this is where it becomes tricky. Do we have nonpolar covalent bonds in HF? How do you know it's a nonpolar covalent bond? Thank you. You have to be able to look at a formula and say what type of bond is present. If you know what type of bond, that can help you classify the compound. If you don't know how to identify your bonds, you will have a bad time. Okay? So you need to go back and review how we classified each of those bonds. A nonpolar covalent bond is a bond between two nonmetals where those metals are, or nonmetals, are the same thing as each other, which means the difference in electronegativity is by definition 0. And one extra rule of thumb, carbon bound to hydrogen. Is HF a nonpolar covalent bond? No. So HF then doesn't fit very well in our nonpolar covalent bond situation, okay, and is best slid into our everything else category as our weak electrolyte. Anybody have any problems with those? Now is your time to bring it up, because I'm going to throw a question at you that will counter everything I just said. No? Nothing? Okay, so I'm going to assume you understand what's going on. What type of bond is between oxygen and hydrogen?
Hydrogen bond.
Not hydrogen bonding. Hydrogen bonding is a force. Dipole-dipole is also a force, not a bond. What type of bond is there between oxygen and hydrogen? It is a polar covalent bond. It is not a nonpolar covalent bond because nonpolar was same to same or carbon to hydrogen. Oxygen to hydrogen does not fit the nonpolar covalent bond category. Does it fit the ionic bond category? Nope, because the ionic bond means metal and nonmetal, which means the OH bond is polar covalent. I gave you the opportunity to ask the question, but now it's coming back to you. Oxygen to hydrogen bond is a polar covalent bond. Why is it in the weak or the non-electrolyte category as opposed to the weak electrolyte category?
You could rewrite it as C2H6.
I could rewrite the formula. It's not going to change that the bond is still between oxygen and hydrogen. Nice attempt to dodge. It does also have nonpolar covalent bonds, but that's still not going to help us out.
There's no cation to make ions.
Still not quite going to help us out. Our rule was our nonpolar covalent bonds. We need something to help differentiate here. Our everything else should really include our acids. Anything acidic should go into the everything else category. Okay. When we're looking at our nonpolar covalent bonds, we can expand that to kind of include our polar covalent bonds that are not acids. Okay. You think this is convoluted? It's because it is. Typically, how do we identify electrolytes? Those of you that were in lab already did this. How do we identify our electrolytes? Conductivity. We test it. We go to lab, we stick some probes into it, and we see if a light comes on. If the light comes on, electrolyte. Light doesn't come on, non-electrolyte. Okay. Are there cases that are going to be counter to what we've explained so far? Yeah, absolutely. Okay. What we're trying to do is come up with the best grouping that we can. Things that are aqueous will very typically classify as strong electrolytes. Things that are not aqueous, say solids, will typically classify as non or weak electrolytes depending on your definition. Weak acids will classify as weak electrolytes. That's a nice one because the weak matches. Okay. Our polar covalent and our nonpolar covalent bond structures will typically classify as non-electrolytes. Okay. And it all comes down to this nasty typically term. Okay. We're trying to work the best that we can within these solutions, but ultimately it's an experimental device that we are then putting a rough definition on top of and hoping for the best. Okay? Questions? Okay. Now into arguably my least favorite section. Gases. Super exciting. So, when it comes to gases, your textbook's going to list out a whole bunch of different rules. There's Charles' law, Boyle's law, Avogadro's law, some other guy's name, law, and I think maybe even a fourth or fifth one. Okay. Ultimately, all of these rules come back to a single expression. Okay. So there's really very little reason to look at each of those individual rules and laws and expressions because there's really only one expression out of the whole process. All of those other individual named rules, okay, were used to generate one expression that covers everything that you would ever need to know about gases. Okay. Which, anybody have the name for it? I had a chemistry teacher insist on calling it PIVNERT. Okay. PIVNERT solves everything when it comes to gases. Okay. P standing for pressure. V standing for volume. N standing for, yeah, I can't explain that one. Moles. T standing for temperature, which is a really long word. And R standing for, it's another weird one, a constant. What's the fun thing about constants? They're always the same. Right? So if you look at each of the individual rules or laws that these people came up with, they're all based out of this equation and looking at this representation all the way through it. Okay? How is that particularly helpful? Okay, well, what we can do is rearrange this equation a little bit to solve for that constant. Regardless of your situation, the relationship between pressure, volume, moles, and temperature will always be a constant. What happens if I change the pressure? Say to go pressure number 1. Well, I'm going to have a volume at that pressure. I will have a moles at that pressure, and I will have a temperature at that pressure. if I now go through and change the number of moles, N2, and I leave the temperature constant, what would my new temperature be if I leave the temperature constant? The same. Didn't have to be tricky. And I leave the pressure constant. What would the pressure be? Can I leave the volume constant? Okay. If I change the number of moles, one of those other terms must also change, because the relationship must always come out to be the same value, whatever that value must be. Okay? Which means I will end up with a new volume. And I just lost connection. Please connect. Thank you. And of course it's not going to draw it. Here's my new volume. I know that the relationship between these two things must be the same thing, which then means, how can I simplify this equation? The temperatures cancel because they're the same. The pressures cancel because they're the same. And I have a new expression, or a new relationship. This relationship shows me the relationship between the moles of a gas and the volume of a gas, known as Avogadro's law, I believe. Okay. All of the individual laws come out of the relationship back to the gas constant. It's when it's actually quantified and we can manipulate and use it. Okay. Which means that I pretty much skip over all of those individual relationships. We'll talk about them to try and think about what they mean relative to each other. Okay? But that's about as far as we'll go. Mathematically, this is where all your relationships fall. Okay? So, some properties of gases. Variable shape, variable volume. We know this because we talked about it in that first week of class. Okay? Gases can expand and compress uniformly. Meaning when we compress our gases, they will all compress evenly. We aren't going to have one section where the area between particles is different than the area between particles in another space. They all shrink evenly and uniformly together. They have a relatively low density. Okay? We can see this because if we look at gases with relatively low density, they tend to be where? Everywhere. Okay? If I bubbled a gas into a solution, we would see the gas sit where in the solution? Typically above the liquid. Do you ever see the liquid or the gas underneath the liquid? Typically not. Okay. The other thing that we'll evaluate is that our gases will mix perfectly and uniformly throughout your whole solution. Okay. And by solution, that's wherever the gases are contained. Okay. One extra thing that kind of comes out of this is that gases do exert a force on the container that holds them. Is that really true? If I put gas into a balloon, what happens to the balloon? It expands. Why does it expand? It's the force of the gas pushing on the balloon. Okay, so there is this force that gases are contributing, which may seem odd because we walk through air. We are constantly interacting with gas, and we don't constantly feel like we're being pushed around. Okay, until we get wind or something else. Okay, but we do have this force contributing from our gas particles. Okay, what becomes fun with that is that we then want to evaluate how we can look at these gases in a simplified fashion. So we've introduced this concept of an ideal gas. Okay? It matches certain assumptions that we're making about our gases, and those gas assumptions we hold to be true, which allows for our equation representations to become relatively simple. If we don't assume these conditions, it makes everything calculated afterwards severely more complicated. right? So some of the big assumptions, probably the biggest one, each particle has no volume, which is kind of an odd statement. Okay? That would be saying that you, as a person, occupy no space within this classroom. Okay? Can I move everywhere within this room? No. Why can't I move everywhere within this room? You are blocking physical space. I cannot exist in the same space that you are in. Okay? When we deal with gases, we're actually assuming, yes, you can. Okay? We've removed the volume equation from our gases. This becomes important because as I come in here, well, usually there's a few of you in here. The first person through that door now can be anywhere they want within the room. The second person through the door can be nearly everywhere they want except where the other person is. So what happened to the volume? It decreases. So every time we add particles into our system, our volume would decrease. Is that going to make our calculation kind of a pain? Yeah. So what do we do to fix that? We get rid of it. We assume that the particles do not occupy space, which means what happens to our volume? It stays constant throughout our entire relationship. Okay? That makes calculations a lot easier. This also brings up this stupid equation that is mentioned in Chapter 8, and you use a little bit in Chapter 9 that I told you to ignore. Now we can't ignore it. You are going to get tested on this relationship. Again, I cannot stress enough how stupid this relationship is. Okay? But you are responsible for using this conversion factor. Because our particles do not occupy volume, it doesn't matter the size of the gas molecule. If I stick the same number of gas molecules into a container, they will occupy the exact same volume. Okay? This is kind of a neat relationship because now I can say 1 mole of particles will equal the same volume. Which again is kind of counterintuitive. The only reason this works is because we're saying each particle has no volume. Okay? Which is kind of relatively true. When we look at a gas solution or a gas system, all of those particles are incredibly far away from each other. The odds that they would ever even attempt to be in the exact same space are very, very small. Okay? So by putting in more gas particles, we don't really see an effect of the particle themselves taking up a larger volume, which then means 1 mole of gas will always come out to the same volume, 22.4 liters. Okay. The reason why I think this relationship is dumb is that this only applies to gases. If we think back to that important equation that we said at the beginning, when we looked at our gases, it came down to one expression, Pivner. Pressure, volume, moles, and temperature are 4 variables within this. When we're looking at a mole of a gas and our liters, we're only attributing 2 of those variables. Okay? So what happens with those last 2? Sort of. We can't just forget them. For this equation to be true, they must be the same. Okay? Because if I take a mole of particles and change the volume, or change the pressure, that's going to change the volume. If I change the temperature, that's going to change the volume, because that's what that expression shows, that pressure, volume, temperature, and moles are all interconnected. So that if I'm going to try and come up with an expression that shows me a relationship between moles and volume, I must keep temperature and pressure the same. This is where this idea of STP comes in, which stands for standard temperature and pressure. Okay. So here's our fancy little equation they tell you is this great way to relate moles and volume, but it only works for gases, and it only works when you're at standard temperature, and it only works when you're at standard pressure. You've got 3 conditionals stacked on top of this. What is standard temperature? Okay. The shrug is not a bad idea on this case. Okay, as I have found many a time when working with my wife trying to figure out their equipment, standard temperature is whoever built the equipment, what they decided standard temperature was. Okay? Completely stupid and nonsensical, but that's how it's worked with. When you talk within this classroom or within most chemistry classrooms, our standard temperature is 0 degrees Celsius. Okay, so we had 3 reasons why I didn't like this equation. We just dropped in a 4th because standard temperature depends on who changes depending on who you're talking to, be it a chemist, a physicist, or an engineer. And now we have a 5th reason. How many experiments are we going to run at 0 degrees Celsius? Virtually none. So we've got 5 reasons why this relationship is stupid. Okay? Last one, pressure. Conveniently, pressure stays relatively constant. Okay? Almost everybody picks the same pressure. Okay? What is that pressure? Atmospheric pressure. So whatever the pressure is, wherever you exist. Well, thankfully, the pressure on the planet is constant throughout the entire area. No. Wow. So really, we've got an equation that works only when 6 different conditionals apply. When do we get 6 different conditionals to say all one thing? On a test. That is it. The only reason we're telling you this expression is because we're too lazy to specify all the other information that you would need to solve the problem correctly in any real-world environment. That said, we still test you on this. Okay? So you still need to be able to manipulate and use this term. When it comes to the final, if you are converting for gases, volume and pressure, or in volume and moles, you are at STP. Okay? So if you see this little statement, at STP, all they're trying to do is say, we're making the equation easier for you, you just had to have this thing memorized. Okay? So memorize this stupid relationship. Okay? And yeah, thankfully I recorded all that. That's awesome. Okay? Low density. Part of this low density goes back and applies to this no volume. As long as we're in a system where we don't have a whole lot of particles, okay, all of these relationships hold true. But what happens is we cram more and more particles into the same space. It becomes more and more dense, and as it becomes more and more dense, are our particles really not occupying volume? That assumption starts to get progressively worse and worse. Okay? So one of our systems is when we're working with these, we are working at low densities. That's how it works best. Okay? And then our last part, we always get a homogeneous mixture. Okay, what did homogeneous mean? Completely mixed, evenly, same relationship all the way through. So if you reach in and grab any random 4 particles, when you reach in and grab another random 4 particles, they will be the exact same. Okay? There's not pockets of different concentrations all the way through. Okay? This force that we talked about, we define as our pressure. Yet another reason why I don't like gases. Actually, we'll come back to that in a second. Let's work with the molar volume real quickly. How many liters are needed to hold 2.0 grams of hydrogen gas at standard temperature and pressure? Okay. So let's go through and solve this the way you should be solving it. Okay. Remember I said we had one equation, PV equals nRT. Right? So if we go through and look at this, what are we solving for? Liters. Liters is a measure of volume. So what should we do with our equation? What's that? Almost, not quite, but right idea. Solve for volume. Okay. So you solve for the unit. In this case, I just wanted you to solve generically for our volume. Our volume needs to equal nRT over P. Okay. What was N? Moles. Whoops. Are we given moles? No. So we are going to need to solve for our moles. How do we solve for moles? Kind of, sort of, yeah. Convert grams to moles, and that conversion comes from our periodic table. So are we given the grams of our hydrogen gas? Yeah, we are given 2.0 grams of hydrogen gas using our periodic table and my awesome rounding skills. 2 grams is 1 mole of hydrogen gas, which means we have 1 mole of hydrogen gas. Okay. Are we given the temperature? We are told that we are at standard temperature. What did we say standard temperature was? 0 degrees Celsius. Okay. And we are told, what about our pressure? At standard. Okay. So we'll pick an easy unit to use first, 1 atmosphere. Can we solve yet? What are we missing? R. Okay. One of the nice things about R is it is always constant. Okay. Which means for every gas situation, all we need to do is look up the value for R. Okay. Or memorize the value for R because it's the same across the board. It's a good thing my memory sucks, but let's see what happens. No one's challenging me. Value for R, 0.0821. I actually want to say 1.5. I don't know if that's true. We'll find out here in a little bit. Okay. The next part are the units on R. The units on R will end up being liters, atmosphere, and actually, do it this way, liters times atmospheres per mole times kelvins. So yes, I'm now telling you to memorize 2 things. The ideal gas expression, Pivnert, and R, okay, which I may have left out a 0. We'll see here in a second. 0.08206. Nice. Okay. As opposed to memorizing one relationship. That one relationship works only in certain conditionals. This relationship holds for all things. So if we now go through to start plugging things in, what did we say N was? 1 mole. What did we say R was? I already forgot my units. Liters times atmospheres over moles times Kelvin. What did we say T was? 0 degrees Celsius. Anybody have a problem with putting 0 degrees Celsius into this equation? What do you mean it won't work? I'll kind of accept that. It'll get you 0 as an answer, which doesn't make any sense. We've got particles. They should be occupying a volume. There's another big reason on why it doesn't work. Can't cancel what out? Your units. Your units drive everything. Do your units of temperature cancel? No. When we deal with our gas law, our temperature must be reported in kelvins. How do we convert degrees Celsius to Kelvin? Add 273. Is it necessary to go through and convert it to Kelvin each time? Why do we not just work in degrees Celsius? What's that? But why not come up with an ideal gas constant that's in degrees Celsius? 0 is a possible issue. There's another big one. But we could change R to degrees Celsius. Why not just fold that conversion in? Temperature is it in North Dakota right about now? Maybe. Negative. If we include a negative value in here, what would happen to the volume? You have a negative volume. We can't work with negative terms when it comes to gas laws. They have to be positive. Okay? That's why we have to go to degrees, or sorry, go to kelvins. Which then means we drop in 273 Kelvin here. What's our pressure? 1 atmosphere. Is that unit okay? Yes. What happens with our units? Moles cancel moles. Kelvins cancel kelvins. Atmospheres will cancel atmospheres, and we'd be left with what unit? Liters. Someone want to go through and solve that for me? Actually using the calculator. 0.0821 times 273. Really straightforward calculation. 22.4133. What your calculator spit out liters? Okay. What was our, we could go through and deal with sig figs. I'll even deal with that. Even drop it down to 2 sig figs. Remember that stupid thing I told you that it's dumb to memorize? 1 mole of gas equaled 22.4 liters. You don't have to memorize that relationship because it comes out of using your standard equation for your ideal gas law. If you use the ideal gas law, there is no magic thing to memorize because it will always solve out and give you that relationship. That is the beauty of the ideal gas law. So, whoa, but it's so much easier to memorize that thing. For this class, sure. You want to go ahead and just memorize 1 liter is 22.4, other way around. 1 mole is equal to 22.4 liters. You can see how well I've memorized it. Okay. Fine, go ahead and do that. If you have to move into 151, you're going to be memorizing that and Pivnert and the ideal gas law, or the R constant. If you just memorize the ideal gas law and R, you're done. Okay. You then just apply that same equation every single time. And every single time, it will be correct. It is a beautiful system. Okay? Questions about that?
I guess just the R is kind of confusing.
What do you mean?
Like, it's just another variable in itself.
So I will call objection to your first statement. Okay? It is a variable in itself. No, it's not a variable. It's a constant. It will always be 0.0821 liters times atmospheres per moles times Kelvin. Which brings up an interesting point. I would also make the argument that if we go through and memorize just R, we've memorized the ideal gas law. Why? What are the units on R? Liters, which is volume. Atmospheres, which is moles, which is K, which is temperature. They are one and the same. You memorize the ideal gas constant with its units. You have all of gases, one little compact package. Okay. Does this involve a whole bunch of conversions and all of that? Yes. Okay. But it's all right there. Okay. It's now just a question of using each of those variables or those other experimental values, your volume, your pressure, your moles, and your temperature, and just inserting them into the equation.
So if there's more than 1 mole of hydrogen gas, would you change like the bottom R?
If you had, so R doesn't change.
Okay.
If you had more than 1 mole of hydrogen gas, something else has to change. Either your temperature, your pressure, or your volume. As soon as you change one of those terms, another one must change. Okay? As soon as you change one term in your R expression, moles, temperature, volume, or pressure, you change any one of those, another one must change. It has to change because R is constant. Okay. You have no choice. You change the number of moles, one of the other three is changing. Okay. It depends on your system. If I take a bottle, okay, and I use that bottle and I put CO2 into it, okay, 1 mole of CO2 into a 22.4 liter glass container. If I now put 2 moles into it, what happens to the volume? It stays the same. It's a glass container. It can't change. Okay. By putting those 2 moles in, I'm either going to change the pressure or the temperature. So either the temperature changes or the pressure changes. So let's say the temperature holds constant. What happens to the pressure inside the container? It goes up. Why would the pressure go up when I change the number of moles? If the mole value increases, for R to stay constant, what has to happen? Pressure will also have to increase to counteract that increase because they are on opposite sides of your, what is the line? Numerator, denominator, there's got to be a name for that line, right? Okay. They're on, there we go, the opposite sides of our divider. Okay. What happens if we held the pressure and volume constant then? So pressure and volume cannot change. What has to change? The temperature. How will the temperature change? It has to go down because what does it have to do? It has to counteract the increase in the moles. Okay. So we can use this relationship to predict all of the little gas laws. All of the gas laws are looking at any of those 2 variables and saying what happens when we increase this? What happens when we decrease this? Okay. Yeah?
So when you find R and it's constant, you're not really finding anything else like that.
So R we never really solve for. We use R to solve for the other terms. Okay. So we can then predict one of the other terms from R. Yep.
0.0821 is the actual number that we should memorize, or was it something different?
Yeah. Why 0.0821 and not more sig figs? Typically, how many sig figs do you carry through in an answer? 3. So you really only need to memorize 3. Okay. Okay. We'll come back to that because it's a little more challenging. Here's yet another reason why I have some issues with this. When we look at pressure, okay, we typically measure as atmospheric pressure. It's the general pressure that our gas exerts anywhere in our planet. And what's happening within that is we have a way of measuring that. What we're looking at is how does that gas push down on all of us around us. Okay. Well, does that pressure really matter? I don't know, if we went out into space, what would happen to our shape? We're going to explode. Why would we do that? There's no more pressure keeping us as the shape we are in. So if we go out into space, what happens to everything holding our shape? Pushes outwards, and that doesn't particularly become a pleasant experience. Okay? So pressure is an important thing. It is constantly pushing down on us. And we can measure that, and it was first measured using a glass tube inverted in mercury. So we fill up the glass tube with mercury, we then invert it in mercury. Okay. The only thing keeping the mercury up in the tube is what? A pressure pushing down on the surface of the liquid. Come on, pen. Which then keeps the liquid up in the tube. If there is no external pressure, we remove all of that altogether. What happens to the liquid in the tube? It goes down. Okay, it'll go down so it's no longer present. What happens if we move to a position where we have higher pressure? It moves further up the tube. So someone went through and noted that when they were in different locations or different altitudes, that changed, or that height within the tube changed. So, well, that's kind of interesting. Then they also noted that when the weather changed, what happened to the height within the tube? It changed. Why would that become relevant? Why would someone want to know that when the weather changes, the pressure changes?
Because it'll ruin your experiment.
It's possible. There's an easier one or a different one. Based on the pressure, I can now predict what the weather might do. Okay. Why would that be fun in, say, the past? Well, now you can come out and say, ooh, I don't know, man. I think it's going to rain in a couple days here. There goes, oh, you're full of crap. No one's going to believe you. It rained. They must know magic. Okay. And all it is a simple observation on what's happening with our external pressure. Okay. So how can we then quantify that? Because maybe a small change in the pressure is irrelevant, okay, versus a large change in the pressure. Maybe that large change is what's going to cause a weather event. Okay, so we'd want to know what that large change is. So how do you quantify it? How would you quantify the height of a tube? Okay. Ooh, interesting. I heard millimeters. On the board it shows inches. Okay. It also says millimeters. We're looking at a distance. How many different units are there for distance? A lot. Which means how many different units are there for pressure? A lot. Okay. Which ultimately means you as students would then need to be able to convert between all of those different units of pressure. Okay. Our original units were based off the distance in that height. So they're based off of inches or millimeters in mercury. Okay. Why mercury? What happens if we had a container of water? And remember, the bottom container has to be open. If it's not open, do we have atmospheric pressure anymore? No, it's all closed in. If the temperature dropped with liquid, our solid could freeze. Our water could freeze. Well, if the water freezes within there, can we see any height change? No. Okay. What if the temperature increased? The liquid could evaporate. If the liquid's all gone, can I see the height change? No. And the height change, as the temperature is increasing, what's going to happen to the height? It's going to decrease because why? There's less liquid in the bottom to hold it up. And that will then disappear. So we have to come up with a system that does not respond to our weather well or external environments. Okay? Mercury happens to be a liquid at room temperature, has a relatively high boiling point, and also has a relatively low vapor pressure, which we'll talk about in a little bit. Meaning it stays as a liquid regardless of the temperature. Okay? That's why we initially used mercury. Okay? It stays constant through the whole process. Sorry, was that a question?
Yeah, is that like what meteorologists use?
Yes, they use
Why are they
pressure.
wrong sometimes?
It's not a perfect science. There's a lot going on when you look at atmospheric systems. It is a massive system. We can't just say, oh, the pressure in this one spot changed. That means it's going to rain 6 inches in this spot. Okay. You have to look at a much larger stance, and that then involves the whole globe. It becomes a much more complicated system. Okay. Yeah, there's a lot of math that goes into it. Yeah, it's kind of cool. If you ever have to fly helicopters, apparently you have to become a meteorologist, I've been told. Mercury. One of the things I mentioned real quickly was this vapor pressure. Okay, we use mercury because it has virtually no vapor pressure. Okay, let's say we switch to water. Okay, we mentioned if we left water out on a table, it would eventually disappear. It would evaporate. Okay, and we heard someone mention boiling. We're turning into a gas. If it disappears and goes to an evaporative state, it's going into a gas. So it is phase changing. When do we phase change from a liquid to a gas?
When you have the
What's that?
reaction?
So chemical reaction is one way to do it, but let's do it as a physical change. To initiate the physical change from a liquid to a gas, what do we have to do? Heat it up to what? If it's water, we can say 100 degrees Celsius. Okay. If it's anything else, it would be the boiling point. Okay, so we have that bottle of water. I'm going to steal this for a second. And we opened that up, and we left that here on the table. And we came back in 4 weeks and said no one could touch the bottle. So let's remove that variable. What happens to the amount of water left in the bottle? We opened it. There'd be no water in it, right? Be all gone. Okay, well, that's because it got to the boiling point of water in this room. That's why it went to the gas, right? I mean, it doesn't get to the boiling point of water? Maybe it does outside. Almost? Wait, if we never reached the boiling point, how did it become a gas? What is evaporation, though? That is transitioning from the liquid to the gas, and we said the only place that we can transition from the liquid to the gas is at the boiling point.
That's what you said.
Oh, okay. I'll accept that. That's what I said. When do we transition from a liquid to a gas? At all temperatures, we can transition from the liquid to the gas. And that transitioning from the liquid to gas is measured as the vapor pressure. All liquids have a vapor pressure. What we are saying is we are measuring the amount of gas that transitioned out of the liquid. How much liquid turned into a gas? We can measure that gas as pressure. How much are those particles pushing on their external environment? And we measure that or report that as a vapor pressure. All liquids have a vapor pressure. If we're going to go back to our system here, what liquid should we be using for our experiment? We want a liquid that has what for a vapor pressure? Very small value or a very large value? Okay. If it's large, what does that mean? That means there's a lot of those particles in the gas phase. Well, to measure this height, what do I need in there? A liquid, not in the gas. So if I have a large vapor pressure, what is all my liquid doing? Going to a gas, and it's no longer a liquid in the tube. If it's no longer in the tube, I can't measure the pressure. So a large vapor pressure is not a good option. What do I want instead? A small vapor pressure. I want a liquid that has very little particles going into the gas phase on its own. It turns out mercury happens to fit that bill almost perfectly. Okay? It has an incredibly low vapor pressure, meaning it will stay as the liquid. Okay? What does that mean about, say, its boiling point? What's happening at the boiling point? Fair enough, yes, it boils. Let's get a little more detailed than that. The vapor pressure does increase. Let's be a little bit, I think I heard it over here. You go from a liquid to a gas. That's what's happening at your boiling point. Okay. If I now want to do the opposite of this, I want to take the gas and force it into the liquid. What should I do? Okay. Condense it. How can I condense a gas into a liquid? What about the boiling point? Cool it down. The colder the environment becomes, the more the liquid stops moving and moves into the liquid phase. What else could I change for this gas to get it down into the liquid phase? I could change the pressure. Remember, the whole point of a gas particle is that they are freely moving. A liquid is they're relatively close to each other. A solid is they're locked in place. Okay? So if I want my gas particles that are freely moving to look more like liquids, what do I need to do? Push them down so that they have less space to move, in which case they become more and more like a liquid. So if I can condense that space down, that means I'm going to have a greater pressure. So a big pressure and low temperature will help keep those liquids or that gas down as a liquid. So I've now picked a substance with a low vapor pressure, and we talked about ways that we can keep it down in there physically from the outside. But that's going to change our atmospheric reading. Okay. What other property could we potentially measure to give us some information about our vapor pressure or allow us to predict it? Okay. Having a high vapor pressure means what about its boiling point? It's very, very low, because a high vapor pressure means we have lots of gas, which means our boiling point is very low. Most of it is going up into the gas phase. Okay. If we have a low boiling point, what does that mean about the intermolecular forces holding all those molecules together? The forces, which will be weak forces. The stronger those forces, the more energy I would need to get them to break apart. So I can now move to a very weak force system. But when you look at a molecule, you don't see the forces. All you see when you look at a molecule are the bonds. So now that I know I need weak forces for a high vapor pressure, what would I expect for my bonds? If I want weak forces, what kind of bonds would generate weak forces? London dispersion is the weak force. The bond generating that would be our nonpolar covalent bonds. Vapor pressure is an awesome question because it takes you from vapor pressure, do you understand what the vapor pressure is, to boiling point. You understand what the boiling point is, to forces. You understand what the forces are, to bonds. Okay. There is a question in the practice exam that does exactly that. It's a lovely question that goes all the way through that. And what you are trying to do is interpret each of those definitions all the way down until you can now look at a structure and say, that has nonpolar covalent bonds, which means that has weak forces, which means low boiling point, which means high vapor pressure. Okay. Neat little system. When it comes to our gases, or measuring our pressure, we want that high vapor pressure, the part that makes this even more confusing. Inches mercury, centimeters mercury, millimeters mercury, torr, psi, kPa, atmosphere. What are those all units of? Pressure. You'll notice the numbers in front are all different because somebody came up with a different arbitrary system to define pressure. Once they had that different arbitrary system, they said they were important enough that everybody had to listen and do exactly what they said in determining those pressure values, which then means you as students get to convert between all of them. How many of those do you need to memorize? None of them. Okay. I would actually argue you kind of need to memorize one. One atmosphere. Yay, one atmosphere. Okay. If you move into 151, you will have to deal with all of those conversions. Okay. Again, I doubt anybody will make you memorize any of those. You just have to be able to look them up. Okay. What is this relationship? If I want to convert atmospheres to inches mercury, what is my conversion factor? Someone was saying it over here. 1 atmosphere equals 29.9 inches mercury. I now have a conversion factor between it. What if I want to convert psi to kilopascals? 14.7. Where'd it go? PSI equals 101 kilopascals. We now have those conversion factors. You can then set that up as an expression within your conversion to get across to that different unit. Why do you want a different unit? Because some stubborn prick, that was a little too fast. Some person did not want to change to a standard unit system. So we end up with 50 billion different units. Are there more units? Yeah. There's a lot of different units for pressure. So watch out for that. You just kind of have to pay attention to it. When you work through questions in the textbook, they'll probably have you go through and convert a myriad of these things between different systems. Why do we want to memorize atmospheres? I did see it. There's a couple big reasons. Pivnern. Our R value was in atmospheres. Could we use an R value in any one of the other units? Yeah. So we could go through and deal with a whole new R value as long as we converted all the units across. It's a bit obnoxious. But our standard one is in atmospheres. What's the other reason why we'd want to memorize our atmosphere as our standard pressure? It's the easiest one to memorize because it's 1. Okay? So we did at least think of it a little bit and made that the easiest pressure to work with because it's our easiest unit.
If torr is defined as 1 millimeter of mercury, why do we need both?
Because some person went through and said, I'm not changing my unit system. This is the unit system I'm going to work in. Okay. One of the kind of complex histories behind chemistry is that chemistry was not just someone in a group of people sat down and said, oh, let's make chemistry. You had probably hundreds of thousands of people with various language, various backgrounds, various histories going through and developing the different concepts that we work with today in different areas, okay, simultaneously. Since they could not communicate until much later, they built a culture and a history around a particular unit. What happens when you get two cultures that are different near each other? You get massive differences, which in some cases we can treat well and we can get along happily. Most cases what happens? War and all sorts of other nasty things happen. Okay? At least scientists said, fine, we just won't agree, we'll just make everybody deal with the conversions. Okay? So we'll pick up there for the last like 3 or 4 slides.